In this lesson, we want to talk about graphing techniques, and here specifically we're going to focus on reflecting a graph across an axis. All right, so in our last lesson, we discussed the concept of stretching or shrinking a graph. Now we're just going to go a step further and discuss the next type of transformation. This is where we're going to reflect a graph across an axis. So we're going to begin today by looking at our square root function. So we have f of x equals the square root of x. This is a function that at this point you've probably committed to memory. If you haven't, it's something you should commit to memory because you're going to see it a lot. Okay, so let's just get some ordered pairs going, or some points if you want to call it that going, because we need to compare them to something on the next page. So I know my input x, I'm going to plug something in there, I'm going to take the square root of that, and I'm going to get my output y, or f of x. So if I plug something in for x, I want it to be a perfect square, so I get a nice clean answer. So I'm going to start with 0. Take square root of 0, I get 0. Then 1, take square root of 1, I get 1. And then for 4, I would get 2. For 9, I would get 3. And then for 16, I would get 4. Okay, so kind of looking at this, I've already plotted the first 4 points. I can't fit 16, 4 on the graph. It's just too small, right? It's just going to be cut off. So if I look at 0, 0, that's going to be here. And then 1, 1 is here. And then 4, 2 is here. And then, of course, 9, 3 is here. So these are the points that you should kind of commit to memory, so that you can quickly graph this kind of square root function, okay? And it's already done for us, so I don't need to trace over it. You just need to understand the general shape of this guy. Now, suppose we introduce something g of x that looks very similar to f of x. So first, let's study these two functions. So we have f of x, again, it's just the square root function. It's the square root of x. And then g of x is now the negative of the square root of x. So this part right here and this part right here, those are going to be the same. The difference is this negative out in front. So really, based on this, I could define g of x as being this negative of f of x, because f of x is the square root of x, and here I have the negative of the square root of x. So this is the negative of f of x. Now, how is this going to kind of affect or change the graph when I have this negative out in front? Well, let's make a table of values for each one, and then we can compare the two. So we know this was 0, 0, it was 1, 1, it was 4, 2, it was 9, 3, and 16, 4. So what's going to happen here, I plug something in for x, I take the square root, okay, so that was my original output here, but now I need to take the negative of it. So there's an extra step. So essentially for a given x value, the y value will be its opposite. So let's copy these x values. We've got 0, 1, 4, 9, and 16. And then just take these corresponding y values over here and change them into their kind of opposite. So the negative of 0 is just 0. The negative of 1 is negative 1. The negative of 2 is negative 2. The negative of 3 is negative 3. And then the negative of 4 is negative 4. All right, so kind of looking at these two tables here, we should get an idea of what's going on. Essentially, for the same x value, I now have two different y values, okay? So I have one that's positive and one that's negative. So let's look at this graphically. And what we see here is that this is the original guy right here. This is my f of x equals the square root of x. Then this guy down here, let me just change colors. This is my g of x is equal to the negative of the square root of x, okay? Or again, you could say this is g of x is equal to the negative of f of x if you want to define it that way. That's fine. What we see here, again, for a given x value, let's just say I have an x value of 4. I now have a y value of 2 and then also negative 2, okay? Negative 2. So what happens is you can think about this as if we flipped the graph or folded the graph over the x-axis, okay? And this is what is known as kind of reflecting the graph across the x-axis. I took this original guy here in orange and I flipped it over the x-axis, or I folded it over the x-axis. And so it creates what's known as a reflection across the x-axis. So let's look at another scenario now. So suppose we have f of x and g of x, and now g of x is defined just a little bit differently. So f of x is the same as the square root of x. It's the square root of x. But now g of x is the square root of negative x. So this is a bit different. Essentially, this negative is what's making it different, So really, I could say if I plugged in a negative x for x in that function, I'd have my g of x, right? So I could now define g of x by saying it's what? It's f of negative x. Again, if I take a negative x and I plug it in for x, I'm going to have my g of x. G of x is the square root of negative x. Okay, so now that we understand that, let's think about what's going to happen with this guy. So again, these guys we should know by memory. 0, 0, 1, 1. We have 4, 2. We have 9, 3, and 16, 4. So what's going to happen is, again, I'm going to plug something in for x. I'm going to take the opposite of it now before I take the square root. Well, I want you to think about the fact that with this guy right here, it's defined for x values that are greater than or equal to 0, right? I can't take the square root of something that is negative in the real number system. Of course, we can do it with kind of complex numbers, but we're not working in that kind of frame right now. For this guy, I've got to think about the fact that this one right here is going to change things. I plug something in for x, I take the opposite of it. So really, I'm going to be restricted to values that are going to be 0 or less. So 0 or less. So we can say that x needs to be less than or equal to 0 here, okay? So thinking about that, what's going to happen is for a given y value, now I'm going to have kind of the opposite x value. So if I copy these y values down, 0, 1, 2, 3, and 4, what I can say is that this would still be 0 because the negative of 0 is just 0. This guy would now be negative 1, this would be negative 4, this would be negative 9, and this would be negative 16. And if you don't believe me, try that out. Let's say I plugged in a negative 1. The negative of negative 1 is 1. So I would have the square root of, again, the negative of negative 1. So that would give me the square root of 1, which is 1. Okay, so that's how I get my answer there. If I had the negative of negative 4, okay, of negative 4, that becomes the square root of positive 4, which is 2. So that's how I get that answer there. So on and so forth. So this kind of negative that's plugged in here with this x, what it does is for a given y value, now I'm going to have the opposite x value. Okay, so let's look at this graphically. So now this graph is going to be reflected across this y-axis. Okay, and again, when I say reflected, you could just think about folding the graph. So if I start with this orange graph here, if I fold it across the y-axis, I'm going to end up with this guy over here. That's what we mean when we say we're reflecting it across the y-axis. It's a folding or flipping a graph over the line of reflection. In this case, the line of reflection is the y-axis. The main thing here is to understand that for a given y value, I have x and then negative x. So let's say I take a y value of, let's say, 3. Okay, so here's 3. So I have an x value of 9, right? 9 with this point here. And then I also have an x value of negative 9 with this point here. Okay, so that's what you need to understand. When you reflect over the x-axis, you're going to have for each given x value a y and then a negative y. Okay, when you reflect over the y-axis, for any given y value, you're going to have an x and then a negative x. Okay, and let's break this down to a general rule. So as a general rule, if g of x is equal to the negative of f of x, so notice how this is outside, it's the same as the graph of f of x reflected across the x-axis. So again, that just means folded across the x-axis. So if you have f of x, and on that f of x you have x comma y, well then on g of x you're going to have x comma negative y. Again, here was that scenario, right? This was reflected across the x-axis. For a point on f of x, like let's take this point here, where it is 4 comma 2, so this is 4 comma 2, on g of x, the same x value, which is 4, now corresponds to a y value that's the negative of this one, so it's 4 comma negative 2. So that's what that means. Now, alternatively, if g of x is equal to f of negative x, so notice how this is inside now. This is the same as the graph of f of x reflected across the y-axis, okay? So if you have f of x and there's a point on there, x comma y, well then for g of x, it's going to be the negative of x comma y. And again, we saw this right here, right? And I already showed you this. So for this given y value of 3, you have this point here that is going to be 9 comma 3. And then you also have this point here, which is negative 9 comma 3. So for that given y value of 3, you have -9 and you have +9 as x values that are kind of associated with that y value of 3. All right, so let's suppose we wanted to work with g of x is equal to the negative of x squared. And for reference sake, I included this f of x equals x squared, our squaring function. As you kind of progress, you're just going to be given one function. You have to kind of pair it up with this parent function. This is one that you're going to know. You're going to have it committed to memory. Again, this is the squaring function. So essentially, I can define g of x as being the negative of f of x. Notice how this guy, again, is outside, okay? It's multiplying the outside. So the negative of x squared. So how can we graph this really quickly? Well, essentially, I know that by rule, if I go back up, if g of x is equal to the negative of f of x, it's the same as the graph of f of x reflected, or again, folded across the x-axis. So all I need to do is graph f of x equals x squared, and then just flip it over the x-axis. So I've already kind of done this, and essentially you should know what this graph looks like at this point. This is, again, my f of x equals x squared, and this is going to be my g of x, which you could define as negative x squared, or you could say negative of f of x. Either way is fine. But essentially, you'll notice that this graph is just folded over the x-axis. So it's folded over this guy right here, or you can say reflected across the x-axis. And again, all you have to do is, if you know this graph by memory, just take these kind of points. 0, 0 is going to be on there. You know that. But let's say I take something like this 1, 1 here. Let me highlight that. Well, I know that for a given x value, now the y value is going to be its opposite. So instead of 1, 1, now it's going to be 1, -1. So I have that. So instead of -1, 1, it's -1, -1. Right, so on and so forth. So this guy right here, instead of 2, 4, it's 2, -4. Instead of -2, 4, it's -2, -4. And you can do that, get enough points going, and you can quickly sketch your graph. All right, so let's look at one that's a little bit tricky. And this is going to come up again in our next lesson. But suppose we have f of x equals 1 over x, and g of x equals 1 over -x. So how can we define g of x? So g of x is equal to what? Is it the negative of f of x, or is g of x equal to f of -x? Let's think about this. Again, f of x is 1 over x, and g of x is 1 over -x. Okay, so if I plugged in a -x there, would that get me here? Well, yeah, it would. G of x could be defined as f of -x. Now, you might see that and say, okay, I'm done. But there's an extra thing here. Because this is a fraction, I could also define it this way. Okay, why does that work? Suppose I said that I had the negative of 1 over x. Well, really, this just means that I have what? I could have -1 over x, or I could have 1 over -x. Both of those would really be -1 over x, because a negative in the numerator with a positive in the denominator, or kind of flipping that, a positive in the numerator and the negative in the denominator, doesn't matter. As long as one sign is negative, one sign is positive, you're going to end up with a negative overall. So you can actually define this function either way, okay? And we're going to talk about this scenario in the next lesson when we talk about even and odd functions. For now, you can just grab either method you want and kind of sketch the graph. It will work out either way. So let me show that to you. So this is our graph kind of pre-drawn. This guy, again, is f of x equals 1 over x. So that's the orange. So you have this, and then you have this over here. Okay, again, because of the way this guy reacts, because you have this x in the denominator, you can't ever get an x value of 0. So that's why this guy has this behavior. As you get closer and closer to 0, kind of going towards 0, coming from the right, going to the left, you notice the y values get really, 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 really big, right? They approach infinity. Because as I'm dividing by something that's kind of getting closer to 0, you can think about dividing by something really, really small, like 0.0000, let's just say 1. If I divide 1 by this number, it's going to be a really big number, okay? And I can keep making that infinitely close to 0 as far out as I want, right? So I can make this as high as I want. Or over here, if I think about it in the negative direction, I can make it as low as I want, okay? The other thing also, you'll see that this guy approaches a y value of 0 but doesn't touch it. And from this direction, it also approaches a y value of 0 and doesn't touch it. And that's because 1 over x can never be equal to 0. Okay? If I'm going to get 0 as a result of kind of this fraction here, well, 1 is fixed, right? I need for 0 to be in the numerator and for the denominator to not be 0 to get this result. Okay, and that's never going to happen. So getting 0 as a result for 1 divided by x is impossible. Okay, so that's why this function kind of looks like this. We've talked about this previously. But now what we want to do is reflect it over either the y-axis or reflect it over the x-axis. Again, it's the same either way. So I'm going to say this is, let me kind of use a different color. I'm going to say this kind of pink color is my g of x is equal to, and we'll start out by just saying it's negative 1 over x. So this is, and let me define that a little bit better. So the negative of f of x. So this will cause us to reflect this guy across the x-axis. So this is going to be my line of reflection. And so let's say I take this point right here. This is going to be 1, 1. If I reflect it over here, it would be here, right? This point would be here, 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 and this point would be here. So you can see that allows you to kind of sketch this graph. Now, the other way you could do this, because it can be defined either way, I could also say that g of x is, again, f of negative x. And now it's going to be reflected over the y-axis. Okay? So then for kind of this point, it would go here. This point would go here, right? This point would go here. This point would go here, so on and so forth. So you can sketch your graph that way. The main thing is to understand what's going on here. Again, if it's g of x is equal to the negative of f of x, then it's reflected across the x-axis. If it's g of x is equal to f of negative x, it's reflected across the y-axis. All right, let's look at something really quickly that you might see as kind of a practice question, or you might get this on your test. Suppose that f of x is defined as negative 2x squared minus 5, and then you're given these kind of g of x, h of x, and L of x. So you got to figure out what they are. So g of x is defined as the negative of f of x. And essentially, all they want you to do here is just multiply a negative by this right here, the right side of the function. Okay, that's how you're going to find g of x. So I'm going to say this is equal to, if I multiplied a negative by this right side, just wrap it in parentheses and perform the operation. This is going to run over, but I'll come back to it. So I'm going to distribute a negative to each term. I'm going to have 2x squared plus 5. Okay, that's all it's going to be. So let me erase this and drag this up. And let me do this one now, and I'll do it in a different color. So now we have f of negative x. So what would happen if I plugged in a negative x where I have that x there? Well, the answer to that is nothing, right? Because the negative is going to be squared. It's going to have no effect, right? So essentially, I can just write this as negative 2x squared minus 5. So negative 2x squared minus 5. Essentially, f of negative x is equal to f of x. And there's a special name for this. Again, when we get to even and odd functions in the next section, we'll talk about this specifically. All right, the other one is the negative of f of negative x. Okay, and you might see this. You might be told to graph something in this way. Essentially, what happens here is that first you're going to plug in a negative x everywhere you see an x. So we already know that that results in this. So you have negative 2x squared minus 5. It's the same thing. Then if I take the negative of the whole thing, well, I wrap it in parentheses and put a negative out in front, that gets me back to this first one here. So I already know that's going to be 2x squared plus 5. Okay? So that's what you would do if you get that scenario. All right, so before we kind of wrap up the lesson, I want to revisit stretching and compressing a graph. When we did this lesson, we didn't talk about kind of the scenario where you had a negative number involved. So if g of x was defined as a times f of x, we said that if a was greater than 1, this would be vertically stretched. And if a was greater than 0 and less than 1, it would be vertically shrunk or it'd be compressed. Now, what happens if a is negative? Well, you follow the same rules. You just use an absolute value sign here. If a ends up being negative, you have to reflect it across the x-axis, right? Because let's say I put a negative a there. Let's just say it was a negative 2 as an example. Well, what happens is it's vertically stretched by a factor of 2, but it's then reflected across the x-axis. Another way you can think about this too is, for a given x value, the y values are going to be changing by a factor of -2. Okay, so you can take the old y values and just multiply them by -2. Those would correspond to those kind of original x values in f of x. So let's look at an example of this, and then we'll go on to the kind of horizontal stretching and compression. So suppose we had f of x equals the absolute value of x, and g of x equals -1/2 times the absolute value of x. So again, I can define g of x as being this -1/2 times f of x. So I've got this negative right here. Again, if I had a negative and no 1/2, this is a reflection across the x-axis. But now when I put this 1/2 in here, I know that I am vertically compressing this guy, okay? And that just means you're moving towards the x-axis. That doesn't necessarily mean that I have to move towards from the top towards the x-axis, which is this way. It could also mean I'm moving from the bottom, coming up towards the x-axis, right? Either way is going to be appropriate for that definition. Okay, so let's erase this. I want to compare kind of some tables here. So I know that 0 would be 0, 1 would be 1. We could do -1 and 1. We could do -2 and 2. And we could do, let's say, 2 and 2, right? I plug something in for x. I take the absolute value. I get y. Essentially, anything I plug in here just becomes non-negative. Now, with this guy here, I can take these same x values, so 0, 1, -1, -2, and 2, and I can just multiply the corresponding y values by -1/2, right? So 0, there's no change. Multiply 1 by -1/2, it's -1/2. Multiply 1 by, again, -1/2, it's -1/2. Multiply 2 by -1/2, it's -1. Again, 2 times -1/2 is -1. So let's look at this graphically real quick. And you have multiple things going on because I want to show you that there's a lot of different ways to kind of do this. The first way you can kind of do it is, again, for a given x value, you could just multiply the y values by -1/2. So 0, 0 would still be there, okay? If I took an x value of, let's say, 2, right now the y value is 2, okay? But now if an x value of 2 goes on this guy, the y value is going to be cut in half and it's going to be made into its opposite. So instead of it being 2, multiply it by -1/2, you get -1. So you're down there. And that color is the same. So let me change the color of that. Let me use like an orange so it stands out. And I can use a point over here. So in this situation, I have an x value of 4 and a y value of 4. Now that y value would be multiplied by -1/2. So it would be -2, right? Same x value. Let me change the color again so that it's clear. So that's one way to do it. You can get some points and sketch the graph. The other way to do this, we could compress the graph vertically first. Again, that's a movement towards this x-axis. So in other words, for a given x value, my y value is now kind of shrunk or multiplied by 1/2. So for a given x value of 4, the y value of 4 would now go to 2. Okay, so once you go through and get these points, you can then take this guy right here, this green graph, let me kind of sketch over it, and you could reflect it across the x-axis, okay? Reflect it across the x-axis, and you would get this red graph here, okay? So two ways to kind of go about that. There's no right or wrong way to do that here. You're going to get the same answer either way. You just go with what is more comfortable for you. All right, let's quickly go over the horizontal stretch and horizontal compression again. This is one that was a little bit confusing. So in general, if you have g of x and this equals f of ax, we said in the lesson if a was greater than 1, now you had a horizontal compression. And it doesn't make sense because you have this number multiplying by x and you think that it's going to stretch or grow, but it doesn't, right? Because it's by a factor. Remember this 1 over a, okay? This 1 over a. So what happens is, let's say a was 3 as an example. So I'd have a 1/3 there. What this means is that for a given y value, the x values are now 1/3 the size. So that has kind of the effect of compressing the graph horizontally, okay? And then we said that if a was greater than 0 and less than 1, well, now we're going to stretch the graph horizontally. And the reason for that is you end up putting a fraction in here for a. You have 1 divided by a fraction, so you're going to get something larger than 1. If I plugged in something like, let's say, 1/8. Well, 1 divided by an eighth is the same thing as 1 times 8, or 8. So now let's think about this, and I'll erase that. We don't need this. Let's think about this when we have negatives involved. Well, all I need to do is just kind of say the same thing. I would put the absolute value bars around it. It's the same thing. I just need to reflect across the y-axis now. Okay, that's all I need to do. So to see this, let's take a look at an example. So in our last lesson, we had this f of x equals x cubed minus x. This is a good example to see kind of a horizontal stretch or compression. And then we have g of x now, which is f of negative 1/2 x. So essentially what I'm doing is I'm plugging in a negative 1/2 x here and here, okay? So for the table of values, we can kind of use 0. That would give me 0. If I plugged in a -1, -1 cubed is -1. And then you'd have minus a -1, which is +1, so that's 0. We know that 1 would also give me 0, right? If this was +1, 1 cubed is 1, and I would subtract away 1, so I'd also get 0. And then we worked with 2 and -2. 2 cubed is 8. Then -2 would be 6. So this would be 6 here. And then -2 cubed would be -8. And then minus the -2 would be +2. So this would be -6 here. Okay, so how could we get the values over here without kind of going through and actually writing everything out? Well, again, for a given y value, so 0, 0, 0, 6, and -6, I know the x values can just be multiplied by 1 over this number. Again, don't multiply them by -1/2. You need to do 1 over that number. Okay, very important to remember that. So 1 over -1/2 is the same as 1 times -2, which is -2. Okay, so what I would do is I would take 0 multiplied by -2, get 0. I would take -1 multiplied by -2, and I would get 2. 1 times -2 is -2. 2 times -2 is -4. And -2 times -2 is +4. Okay, so now we have some points going, and this is something we probably don't know the shape of. So if I took these values, I could go to my coordinate plane, and I could very quickly graph this guy. And let's take a look at that real quick. All right, so graphically, you're going to see 3 different graphs here. And I did that to show you the 2 different ways you could do this. The first way you can do this, you don't even need the original one. This is the original one in orange. This is f of x equals x cubed minus x. Again, if you know that, and you're told this is your new function, you can just make your table of values, plot those points, and then sketch the graph. That's all you really need to do. But if you're specifically told that you kind of have to graph the original one and then reflect it, well, then you can use this process here. What you can do is you can horizontally stretch it first. So I can say, let's go with h of x. Let's say h of x now. H of x is going to be f of, and I'm just going to do 1/2 x. I'm not going to include the negative yet, okay? So what that does is it stretches it by a factor of 2 horizontally. Again, it's 1 over this number. 1 over this number. 1 divided by 1/2 is 2. Okay, so it's horizontally stretching it by a factor of 2. So you can see this because a y value of 6 used to correspond to a x value of 2. But over here, the y value of 6 corresponds to an x value that is 4. So it's gone from 2 to 4. So it's horizontally stretched or pulled away from the y-axis by a factor of 2. Now, once you've done that, now we can reflect it across the y-axis, okay? So that's where this graph comes in over here. This guy that's kind of in, I guess you would call this a teal. I might call it a green. I'm not sure what color it actually is. But let's just call this is our g of x. And this is what we're trying to find. This is our f of negative 1/2 x, okay? And essentially, I got this by taking this guy and reflecting it across the y-axis. So notice how this point here goes over here, okay? So essentially, I have what? I have 4, 6. The y value of 6 stays the same, but my x value is going to get kind of the opposite put on it. So you put a negative on it. So you have negative 4, 6 now. So negative 4, 6. And over here, it's 4, 6. Okay. And you can do that everywhere, right? And I'll focus on these ones down here because in the middle, it just gets kind of crowded. But if I focus on this one, this point was negative 4, 6. So negative 4, 6. Okay. Well, what happened to this point is it got flipped or folded or reflected across this y-axis, and it went right there. So now this is positive 4, comma, negative 6. So again, the y-coordinate stays the same. It's negative 6 in each case, but we took this x-coordinate and just made it into its opposite. So a lot of different ways to kind of do this. Either way, you're going to get the same result. Some of these graphs do get kind of involved, but for now, in the section we're in, it's pretty easy overall.